Recording. Okay. So before, first of all, everybody got A in midterm. Good job, everyone. But there were some carelessness, so you caught them off points, but thankfully, not too many for any one individual. You should have be able to see the feedback in Canvas comment about how many points were lost in any problem and why. And when referring to a problem, like I just say, like 3, that's a problem 3, whereas if I say like L1 or L2, that's lightning round problem 1 and 2. So to distinguish between the 2. Okay, now, before I get to today's topic, I want to give some context where we're at in the course as a whole. Okay, so what we've been doing all semester long is how to solve a system of linear equations A x equals b. And I think it's safe to say, especially for an advanced undergraduate or beginning graduate class, we've very much beaten that problem to death. So what we're going to move on to now, where we're headed, is how to solve systems of nonlinear equations of a form that's a vector value function f, and that takes a vector as an argument x. We'll see where it's equal to 0. So in this case, x is a vector in Rn, and f is a function from Rn to Rn. The vector comes in, vector of same dimension comes out. Okay. You can also think of f as like a vector field. Well, that interpretation doesn't really mean much for this class, as opposed to like multivariable calculus. Okay. Now, because when we get to systems, we'll learn about generically how do you solve a system of nonlinear equations, and then toward the end of the course, we'll be particularly interested in systems of nonlinear equations that arise from solving differential equations. Like we're solving a system of ODEs, like for initial value problem, and also for a boundary value problem. Once we discretize, that can lead to a system of nonlinear equations to solve. Now, keep in mind that this is the second course, in the 2-course sequence in numerical analysis. Now, of the 5 of you, 4 here and 1 online, only 3 of you were in the predecessor course last semester, and then 1 took it the last time it was offered, the previous time it was offered. That would have been back in 2021, and then if 1 of you has not taken that particular class at all, but may have taken something equivalent elsewhere. So, so before getting to systems, what we're going to do for this class and the next class, and so even those of you who did take the class last semester, it's just easier to assume that things have been forgotten. That makes running the class much easier. How to solve a single equation, a single nonlinear equation of x equals 0. So what we're going to do is, now in that 465-6b, I cover 4 different methods for solving a single nonlinear equation, but only 2 of the 4 actually have a straightforward generalization to a system of equations. So it's just those 2 that I'm going to revisit. The fixed point iteration today, and then on Monday, Newton's method. And then, so that's chapter 10, and then we get to chapter 11, where I'll talk about both of those methods for a system, and then we get to differential equations. So, So for those of you who still have the last semester's material fresh in your mind, I apologize for any more that may ensue, and I'll try to do my best not to accidentally do any homework problems at a time. I should mention, speaking of homework, if I look at, okay, so I'll flip over to Canvas. Okay, I'm actually going to visit. So this is that's type of 46560 from last semester, and so the problems that you have done for this section I'm covering today, 10.3 on fixed point iteration, are only problems 3 and 4. But if we go to Canvas, and some assignments, and then I just posted homework 5. Okay, so those 2 problems from that homework, I guess it gets turned in again. But there are 3 more that are new. And that kind of ones where it's actually involves proving something. I always love to prove it in class, and I just tell myself, don't do that. So, maybe I'll last semester though. I'm not sure. Okay. Well, we'll see. Someone's gonna find out. Okay. And then it'll be a similar review. So homework 6. Okay, so from the Newton's method. Yeah, some of these problems were assigned last semester, but not all. So, okay, I call this a review of fixed point iteration Newton's method, but I guess it's not how to review it. No. Okay. All right. So, fixed point iteration. So the idea behind fixed point iteration, also known as successive substitution, is if we're trying to find a root of a function, f of x, then we can just take this equation and algebraically write it in this form, x equals g of x. Now, like I said, there's so many ways that can be done. The easiest way is, actually I'm going to change this plus to a minus just because of the notational convention. That if I define g of x to be x minus some non-zero constant times f of x, then you can show that g of x equals x if and only if f of x equals 0. So the 2 equations, so this equation and this equation are equivalent in that case. And that leads to the very simple algorithm for fixed point iteration. You choose some initial guess, which we'll call x0. So like with iterative methods for x equals b, I'll use this superscript notation. The superscript in parentheses refers to the index of an iterate. So I'm generating a sequence of iterates, x0, x1, x2, and so forth. And a way to get each new iterate is by substituting the old one into my function g, because if the iterates converge, then I'll just have the equation x equals g of x, which is what I'm trying to solve. So I generate my new x, I examine the 2 x's in some way to check whether I'm converging. For instance, I can check whether the latest x and the previous x are close in absolute value, like within some, the difference is less than some error tolerance. And then, so I'll keep computing the new x and keep checking for convergence until it's over. If convergence happens, it's a good idea to impose some sort of maximum number of iterations. That way your loop is not going to run on forever, because as you'll see in some of the examples I'll do today, fixed point iteration or successive substitution can most definitely diverge. So I'm going to look at some examples in MATLAB. Okay. So in these examples, I want to basically compute x equals g of x. So I can define g to be a function handle. So And I do that by using this notation. I use the at sign, and then in parentheses, I indicate the arguments of a function. Now, g is just going to be a function of a single variable, x in this case. And then after that, I can define what I want the function to be. Now, this is a good idea if the function is particularly simple. If I have like some really elaborate thing, I should define g using an m file instead, but I have no need to do that here. So in this case, I'll just do g is equal to cosine of x. So I'm going to solve the equation x equals cosine x, or equivalently, x minus cosine x is equal to 0. So this would be my f, x minus cosine x, whereas cosine x would be my g. I'm just going to pick the initial guess. So x equals 1. Okay. And we'll be coming up long. So then I'll just do x equals g of x. And what I'm hoping for is that the iterates will converge some solution. So if I carry out some iterations, they're jumping around a bit. That's not such a good sign. But I'm going to keep going, keep the faith, and see if they do appear to be getting closer. So now at this point, we see that the first 4 decimal places agree. So it is definitely showing signs of convergence. So at this point, you'd be talking, well, when do you stop? Like, how close do you want the iterates to be? Maybe you want very high precision, like degree within 10 to the minus 15, or maybe you don't care for that much accuracy. Maybe you don't need that, and you choose a larger tolerance. I'm going to get greedy here, and just see what it takes to converge all the way to all the digits that are displaying. We see that all but the last 4 digits agree now. It's just taking a while. So this is not a fast method for this example anyway. And now we finally have convergence. The last time I did a diary on this 2 years ago, I have it written in my notes that it took 88 iterations to converge. All right. So that's not good method, and I'll be able to explain why a little bit later on. But first, I want to show you. First, any questions so far? Now, for our second example, g of x is equal to x squared plus 3/16. So the solutions to solve x equals x squared plus 3/16. Now, so that is a quadratic equation. Now you can solve it by hand, but it is just an example to illustrate what one iteration can do or not do. So the roots are equal to roots are equal to 1/4 and 3/4, the 2 solutions of this quadratic equation. So what I'll do is I'll define my function g, be x squared plus 3/16. And then I'll choose 0.2 be my initial guess. Okay, and then I'll do the same thing before, x equals g of x ad nauseum. And we see it's converging pretty quickly, much more rapidly than in the previous example involving cosine. And still not that fast, but so now we're at 0.25, so converged to the smaller of the 2. So it converged more rapidly than for x equals cosine x. Okay. Now I can choose a different initial guess. Now, so it's closer to the other solution of 3/4. So the expectation is that if I carry out iteration this initial guess, you think it would converge to 3/4. Let's find out. Okay. So now it's going the wrong way. It's going away from 3/4. And things are getting a little out of hand. So that was unfortunate. So if I were to continue, we'd see that the inverse would diverge. That's why it's important to have in a practical implementation like in code, then it puts a cap on a number of iterations that it would at least finish gracefully in this solution. It's not much of a difference. 0.7. So it's still close to 3/4, but it's less than instead of greater than. So again, you would think that it would converge to 3/4, the nearby solution. So I'll go ahead and do x equals g of x. And it's going the wrong way again, away from 3/4. I was like, what the heck? And then now it's quickly getting close to the other solution, the lesser solution, no 1/4. And it'll converge. It'll converge to that. So it converges either to 1/4 or diverges. Wherever you plant the initial guess. So an initial guess on either side of 1/4 will converge to that one. But if it's greater than 3/4, apparently it diverges. Okay. Right, so that's the second example to show you. Third example, x plus natural log of x. Now we think of natural log as ln of x, but in MATLAB, use log to refer to natural log. And if you want log to base 10, the MATLAB function for that is called log 10. So I'm going to solve this equation, x plus natural log of x equals 0. Or if I write this in fixed point form, x equals minus natural log of x. So I'm going to define g to be minus natural log of x. Now, to get an idea of what initial guess could be, I'm going to evaluate. So this is equivalent to solving f of x equals 0, where f of x equals the original function I had up here, x plus log of x. So I'm going to, for convenience, I'm going to define f to be x plus log of x. And now I'm going to evaluate this function at two select points. F of 0.5 is negative, and f of 0.6 is positive. So, can anyone tell me, if I evaluate the function at 2 points, and one of them the result is negative, the other result is positive, what does that tell me? In terms of trying to find where the function is 0.
There's a root there.
There, where?
In between.
Yes, in between. I trust that's what you meant. But yes, in between. So, and that's the concept of the intermediate value theorem that you learned about in calculus 1. Solution exists, the interval 0.5 to 0.6. Now, if we look at the derivative, we could learn something more than that. So f prime of x is equal to 1 plus 1 over x, which is positive for all x in the domain. Because log is only defined for strictly positive x. So f is increasing. So if you know that a function f of x has a root in a particular interval, and if you know that the function is always increasing, that root that we're looking for is unique. Because I can mention another theorem from calculus 1. Rolle's theorem. Fa equals fb means that f prime of c is 0, c in between. So if we take like a hypothesis of that, if a derivative is never 0, then there's no way for a function to equal the same value, like 0 in this case, at 2 different points. Okay, so we have this one root between 0.5 and 0.6. So what I'll do is I'll set the initial guess to be the midpoint of that interval. Interval is known to contain a root. Okay, so now I'll do x equals g of x. And define g of x, I just define x equals g of x in the most straightforward way. I just move the log x to the other side. So g is equal to minus natural log of x. Okay. So we're still in the interval. Right, bouncing around a bit, but now we're outside the interval. And that's like on both sides of it. The iterate went negative. Log of a negative number is complex. So the iterates diverge. That's a problem. Okay. So what can we do instead? We examine the equation x equals g of x. Then we have the following. If I take the inverse of g, and because the derivative is 0, the function is increasing, it's 1 to 1, therefore it has an inverse. G inverse of x is equal to g inverse of g of x. But g inverse of g, g inverse and g cancel each other out. That's just x. So we can always say that x equals g, if the inverse exists, x equals g of x is equivalent to x equals g inverse of x. So we just tried x equals g of x, a fixed point iteration, and that diverged. So we can take the inverse of minus natural log. So we need to know what is the inverse in this case. So y is equal to minus natural log of x. I need to solve this equation for x as a function of y. What do I need to do to this algebraically to try to figure out what the inverse would be? Yeah, I'll take the exponential, but first I'm going to negate both sides. Minus y is equal to natural log of x. Then I'll take the exponential of both sides. I'm going to have e to the minus y is equal to x. So that is the inverse. So I'm going to find g to be e to the exponential of minus x and see if that fares better. Okay, so now I have x. I'll set x back to the midpoint, 0.55. Same initial guess. All right, so now do x equals g of x again. See if this fares better. Okay. All right, at least we're staying in the interval. The iterates appear to be getting closer to each other. This one, it's, okay, yes, it's definitely converging now. Bit slow, but it is getting in. Okay. So where one failed, the other succeeded. Questions so far about these examples? Look at convergence theory a little later to see why these examples behave the way they do. But one more. Fourth example, x is equal to cosine x plus 2. Favorite 6-point example. So I'll find g, be my right-hand side function as usual. Okay. Then value for plotting purposes, which I don't have any figure windows open. Yes, I know we're doing computation network, it doesn't need to keep telling me every 2 seconds. So now I'm going to plot g evaluated these x values in this vector, just so we can see what the graph looks like. Okay, all right, so there's a graph for x between 1 and 3. And then what I'm going to do is, on the same graph, I'm going to plot the function y equals x in red. So red is x, blue is g of x. So where they meet, oh, this is a problem. Okay, and then Taylor just got disconnected. The WebEx meeting is still running. Okay. Oh boy.
Is that?
Okay. Ugh. I actually really embarrassed about this. Okay, but okay, I'm going to. Oh, Taylor did tell me that she might step away. Okay. Um, um, all right. So now what I'm going to do is on the same graph, I'm going to plot. Okay, so I can set initial guess in between. So we're doing x between 1 and 3, so I'll just pick a different guess in between. Okay, Taylor says there's no connection. Oh, their Wi-Fi is out. Our Wi-Fi is on. So I'll start my initial guess to be the midpoint. And then I'll plot that as a circle. Okay, so that's where initial guess puts us, not terribly far away from the intersection. So unlike before, I mean, I'm going to carry out the iteration like in the previous examples, but what I'm going to do each time is plot it on the graph, so you can see how graphically how the iteration is unfolding. So I'll do x equals g of x. All right, so that puts us at 1.58, and then I'll plot that. And now we were over here, but now we're over here. So we hopped over the solution, which seems a bit inefficient. And now I'm going to do this again. X equals g of x, and plot. So now I'm back over here. So there's a bit of a hopscotch going on. And if I keep going, yeah, so now you just keep bouncing back and forth on either side of the solution. So like, okay, why? It seems like it's going to take forever to converge, and in fact, it would. I'm not going to do that now. Okay. So that's unfortunate that sort of behavior can happen. So as far as what we observed as a summary, okay, so first iteration, x equals plus minus x, it did converge very slowly. The second example, it did converge to 1/4 unless x is greater than the second root, and this gets diverged. And then for a third example, we have this most straightforward way of writing it as a fixed point iteration, but that diverged. So then we rearrange the equation to get this one, x equals e to the minus x, that did converge. Okay, why is that? And then for last example, we're solving this equation. Now, we saw that it's very slow. But then, if I'm going to, what I could do instead is the picture suggests that if I were to take the average of two consecutive iterates, that would put me right in the middle. Like, would that work more rapidly? So if I go ahead and try that. So we'll go back to our initial guess. And then I'll do x is equal to x plus g of x all over 2. Because if x equals g of x, so that x, then that x will be a solution to this equation also, and something you can algebraically confirm. So keeping in mind that our initial guess was over here somewhere, so I'm going to compute iterate, all right, and then I'm going to plot that, but using a black circle just so you can distinguish. And so here it is. It's like pretty much dead on. So we hop from here directly to here. But now one more time. Okay, still the same territory, and I'll plot. So now all the iterates are clustering around the exact solution. And if I go one more time, yeah, they're all there. And look at the iterates themselves. So here we have the first 4 places after the decimal point agree. And if I do it again, these two are also very close. One more. And yeah, so here we have 1, 2, 3, 4, 5, 6, 7 decimal places of agreement, almost 8. So that iteration works really well. But why should that one work so much more? Well, why should it work so much more rapidly than the original? So we need to have some handle on what makes iteration converge at all, and also what determines the speed at which the iteration converges. Okay. So for that, we will have convergence analysis. So to review that, something that was also covered last semester, Brouwer's fixed-point theorem addresses the existence of a solution to x equals g of x. That if g maps an interval into itself, so any x in an interval AB gives you g of x, also an AB, then a fixed point exists. The proof is actually quite short using the intermediate value theorem. That's one of the assigned homework problems. Now, what about uniqueness? So if G satisfies what's called a Lipschitz condition on the interval AB, so that means that the difference between G values is less than or equal to some constant capital L is called a Lipschitz constant, times the difference in X values, and if L is less than 1, then we say that G is a contraction. So anytime the difference between G values is strictly smaller than the difference between the corresponding X values, then the fixed point is unique. Also, fixed point iteration is guaranteed to converge for any initial guess in that interval. That's called the contraction mapping theorem. Now, we go with a simpler criterion for convergence if a function is differentiable. By the mean value theorem, if I take this g of x minus gy and divide by x minus y, that's equal to a derivative at some point between x and y. So if the derivative exists on AB, and if the absolute value of the derivative is it's going to be less than or equal to the Lipschitz constant, and again, if that Lipschitz constant is less than 1, then we can again conclude that G is a contraction. Now, I should point out, it's subtly here, it's not enough to say G prime absolute value is less than 1. It has to be bounded away from 1 to guarantee a convergence. They're not the same thing, because if we simply have a condition absolute value of G prime of x is less than 1, that means G prime is allowed to approach 1, and that could cause a problem for convergence. But this way, it's less than or equal to some constant L, and L is less than 1, then G prime is not allowed to approach 1. Questions about these convergence statements? So it all boils down to the size of the derivative of G near the solution. So now what I can do is revisit the examples armed with this information about convergence. So for the first example, if G prime is minus sine of x, back to example 1, x equals cosine of x. I evaluate G prime at the fixed point. Now I need to scroll back through here to retrieve that fixed point. Okay, here it is. What I can do is take the fixed point from x equals cosine x, and evaluate the derivative at it, and I want the absolute value. Well, we want it to be less than 1. It is, but it's not much less than 1. So, so the error is not going to 0 all that rapidly. So we need it to be less than 1 to guarantee convergence. But the smaller it is, the more rapid the convergence will be. So this gives an idea as to why the convergence is slow in this case. So G prime is not much less than 1. So convergence is slow. Okay. Now, if I look at second example, okay, so G prime is just 2x. So G prime at 1/4 is equal to 1/2, so that's less than 1. But G prime at 3/4 is greater than 1. So when a derivative fixed point is greater than 1 in absolute value, we say that the fixed point is unstable. So fixed point iteration cannot converge to it. unless you get lucky, like you plug some X in and you happen to land right on that unstable fixed point, okay. But there's no infinite sequence of iterations that will converge to that fixed point when it's unstable. So that explains the strange behavior we were seeing in this example. But it really wanted to converge to 1/4, we could not get it to converge to 3/4. Third example. So x equals minus natural log of x. So g prime is equal to -1/x. And we're on the interval from 0.5 to 0.6. But if we plug x values from here into this derivative, we're going to get derivative values that are greater than 1 in absolute value. So the exact solution is an unstable fixed point for this g. But then we change the equation around instead of using g of x equals e to the minus x. And in that case, so we have minus e to the minus x. But when x is positive, this is going to be less than 1 in absolute value. So another way to look at it, if you take x equals g of x, you try it out, it doesn't work. So then you work the equation x equals g inverse of x. We have this differentiation rule for an inverse function, that the derivative of the inverse is 1 over the derivative of the original, evaluated at f inverse. So if you come up with an iteration x equals g of x, and you find that g has a derivative that's too large in absolute value, then you know from this differentiation rule that taking inverse is going to work. Because if a derivative of the original is too large, the derivative of the inverse will be sufficiently small because you're taking the reciprocal. That's what happened with that example. And finally, back to example 4. So g of x is equal to cosine x plus 2. So g prime of x is equal to minus sine of x. And the inverse I was getting around here, so minus sine, the value of minus sine of that turns out to be near 1. So with g of x equal to cosine x plus 2, g prime is, absolute value of g prime is nearly 1 near the root. So we have convergence very slow. But then, if I have x equals h of x, where h of x is equal to x plus g of x over 2. So h prime of x is equal to 1 minus sine of x all over 2. So if I evaluate that, the value of 1 minus sine of a fixed point, or near it, all over 2. And what do I get? Yeah, so it's nice and small, like 1/100th. So the derivative is actually nearly equal to -1. So by throwing in x, which has a derivative of 1, it's basically canceling it out. Yeah, so here h prime at the fixed point is nearly 0, resulting in very rapid convergence. And I told the story last semester how when I discovered this, because I was creating this example just for the book, and thought, oh wow, what if I design a modified fixed point iteration if I can estimate what the derivative is at my latest iterate, and then I can take a linear combination of g of x with some multiple of x, and basically cancel out the slope. And I called it slope canceling fixed point iteration. And it worked really well. In fact, I proved that it converged more rapidly than fixed point iteration. Like, yes, this is great. I can write a paper on this. And then I discovered that I accidentally rediscovered the CCAT method. So, it might be good, something good to present like in the classroom, but definitely not a research accomplishment. Oh well, it was hard. Now, if we take a Taylor expansion of G, that gives us insight into convergence behavior. So if I have the new iterate, xk plus 1 minus x star, which is the exact solution, well, xk plus 1 is g of xk. X star is g of x star, because x star is the solution of x equals g of x. But then I Taylor expand g of xk around x star. And what that gives me is first couple terms right here. So we have g prime times xk minus x star. So what this is saying, so to translate this into English, the new error is equal to the derivative at the root times the previous error. And then we have some lower order terms that are proportional to the error squared. But what this says is convergence is linear. So the error is roughly proportional to the previous error, and this is a constant of proportionality. And so the absolute value of this, g prime of x star, we call that the asymptotic error constant. So when convergence is linear, it's basically the ratio of errors. So that's what happens in fixed point iteration most of the time, that the error decreases by a factor that's approaching this. So with the first example, with cosine, this was equal to 2/3 in magnitude. So because it wasn't really all that small, that's why the error didn't go to 0 that rapidly. And this also shows me why we want this to be small, as that will give us more rapid convergence. On the other hand, suppose this value, g prime at the root, suppose it happens to equal 0, then this term goes away entirely, and this is the leading term in the error. So now we're saying that the new error is proportional to the previous error squared. That's quadratic convergence. We like quadratic convergence, because if the error is already small, then it's going to get a whole lot smaller from one iteration to the next. You end up having like the number of correct decimal places roughly doubling from one iteration to the next. But that's you'd have to like contrive G to make that happen. Okay. So questions about the convergence behavior? Now, so speaking of trying to like jigger fixed point iteration to achieve faster convergence, leads to a concept called relaxation. Suppose I define g of x to be equal to x minus a constant times f of x. So I'm trying to solve fx equals 0 by solving this. So the equations are equivalent as long as lambda is non-zero. But there's a way that we can choose lambda to make convergence more rapid. So the science of choosing lambda to achieve faster convergence, that's what relaxation is about. So, and this goes to a couple of homework problems. Suppose that the derivative of f is strictly positive. If the derivative at the root is equal to 0, that's actually a problem for root finding methods, because the graph has to be very flat at the root, and it causes iterative methods to converge slowly. So we're not going to think about that case right now. We're going to assume that the derivative is non-zero at the root, or just for convenience, we'll assume it's positive. Now, if it's positive, at the root, then by continuity, it's actually we assume f is continuously differentiable. So really, it's by continuity of f prime, not f. So if it's positive at this point, then for x near that point, the derivative is also positive. So that's just what we get from continuity. So it is possible to show, and you do show it in homework, that it is possible to choose lambda to make this happen. That you can guarantee convergence, and the value of lambda that you get is this right here, and then this Lipschitz constant that comes with it is equal to this, which where little m and big M are lower and upper bounds in the derivative for nearby x, and this is why we use the assumption that f prime is positive, and therefore it's positive nearby. So little m and capital N would also be positive for x sufficiently close to the root. So that would cause this to be less than 1. So at least we see that it's possible to use lambda to make convergence possible. But that's still a fixed choice of lambda for every iteration. Now suppose we allow lambda to vary from iteration to iteration. Then as the iterations are getting closer and closer, lambda is converging to 1 over f prime at the root. So that's just putting g of x equal to x minus f over f prime. And if you were to work out g prime at the root for this choice of g, you would get 0. And that means that this kind of fixed point iteration would converge quadratically. But that's actually Newton's method. So this is one way of deriving Newton's method. You'll see the other way next class in terms of like a tangent line approximation. But fixed point iteration and Newton's method are very closely related, because really you can think of Newton's method as a specific example of fixed point iteration. Designed to get faster convergence than fixed point iteration would get in general. Right. So that's the rundown on fixed point iteration, and later on in the line, I think it's going to be a week from today, is when I'll talk about fixed point iteration or a system of equations, and how this convergence theory about g prime and so forth has to be generalized to the case of a system of equations, using like the Jacobian matrix and all that. Okay, so come to the end of the notes. So do we have questions on anything? Yeah, let's get out of here. Before we hold on a second. Okay, let me just stop.